Yeah, so I'll talk today about optimal prediction in spatial temporal systems. Can the people in the back hear me? Yes, okay, good. That's joint work with my advisors, Cosmo Shalisi and Larry Wasserman, and Eli Marion and Chris Genovese for the applications part. So what is a spatial temporal system? The weather is a spatial temporal system. If you look outside, it's a 3 plus 1 dimensional system. Or if you watch it on TV, you have satellite images. Those are 2 plus 1 dimensional systems. When I say 3 plus 1 or 2 plus 1, I mean 2 dimensions in space, the image, plus 1 dimension in time. That's what I mean with 2 plus 1. And in general, any video data or image sequences that you analyze, that is a 2 plus 1 dimensional system. You have the image, and it's evolving over time. And the 1 plus 1 dimensional system, that's more for illustration, because then I can show you the whole space-time in one image. So you have space vertically, and time goes from left to right. And you can think of like fluid flow simulations that you might have seen before. They typically look like this, right? So that's what we are trying to study. And why do we want to do that? Because all of these systems, right, they look different, but they all have spatial and temporal dependence. So what can we do with this? We want to use the information in this data for 3 main reasons. One is to forecast, that means predict the system in the future. One is discover patterns in the data. For example, well, there's smoke and there's background, there's a candle. And then we want to learn the dynamic laws given the data. So I want to learn that heat rises from the video. Now for a physical process that might be redundant because we know that already, but think of a social process that happens in space-time. There we're not sure yet at what are the laws that generate these processes, so we might be able to detect social laws and social dynamics that give rise to the data we see. The prediction problem is as following. So you have XRT, which is a space-time random field, or a stochastic process, indexed with a spatial coordinate and a temporal coordinate. Again, space can be 1 to n-dimensional, and time is always 1-dimensional. So here you have 1 plus 1d, and here 2 plus 1d. And what is the prediction problem? Well, given the data, given this whole image, or given the entire video of that candle, I would like to forecast what does this image look like in the future. So I want to forecast that smoke will rise when I see this. Or maybe also interesting, I cut off this image here. Well, I would like to predict what does it look like on the left. So that's a prediction problem. For the pattern discovery problem, in the machine learning statistics department, a lot of the literature, a lot of what we do is we develop methods and algorithms that extract signal from the data and remove the noise. But often someone says, oh, I know I want to look for high variance in the data. If you know that, you can use principal component analysis. Or you say, I know I have to look for independent signals. Then you use independent component analysis. Or in fMRI, for the particular applications that I will show, they have often fMRI data, so you scan the brain, and you do this by you show first a person a particular stimulus. But you know exactly what the stimulus looks like. So all I have to do is look at some kind of template matching. Right? You know this is what I'm looking for, so let the algorithm look for that. And you can go on and on and on. A lot of methods work like this. Someone has to decide, oh, this is interesting, make the algorithm look for that. This works well if this measure really captures what we want. If I know the stimulus has a certain frequency, then I just define a filter like this and I get the response. But this doesn't work if you don't have such a measure. It doesn't work if the data is not the way you expected it to be. And it doesn't work if you use the wrong interestingness measure. But who tells me that high variance is really the interesting part? It's the high variance part, but it's not necessarily interesting. However, when we look at some spatial temporal system, nobody gives us an interestingness measure. We just look at it and we see, oh, this is interesting, this is not interesting. For example, if I show you, two spatial temporal systems, here's one of them. Okay. And here's another one. I don't know what interestingness measure you have, but I think you would say, well, the left one wasn't really interesting. And the right one, you could see non-trivial structure. You could see these bands here, and you can see that they are active and inactive. So the idea now is, well, if we can do that, we want an algorithm, a method that can also do that. And you can do it automatically, without me telling it, look for these bands. That's what they currently do, right? They look at the brain scans and say, oh, we know this is the frequency, so look for that. But we don't want to do that. We want to do it automatically. So that's the pattern discovery problem. And previous work for the forecasting is typically time series related, right? I mean, you have a time series and you want to forecast. So you could think of this huge image that I showed you, each row, like the whole row, as an n-dimensional time series. And you fit some high-dimensional time series model to them. And then you make predictions. And we know very well how to make predictions in these ARMA models, Garch models, hidden Markov models. Or you do a time series model for each point separately. So you take each row of this image that I showed you, you model it as a Markov process, univariate, predict it, and then just collect it together. But this will probably fail, or not fail, but it will give you bad predictions. Because in the first one you have recursive dimensionality. I mean, these images are huge, have very large dimensional. The candle video are 10, on the order of 1 million points. So you have to fit a 1 million dimensional hidden Markov model. That won't work. And if you consider each point separately, then you completely ignore the spatial dependence. And, well, we don't want to do it because there's obviously spatial dependence in the data. And another approach, which is actually in this department, is a spectral learning approach of the dynamic system by Boots and Jeff Gordon. And they have these global algorithms that work really fast and predict really well, and they learn the global dynamics of the system. But we also want to learn locally the dynamics. In each pixel, we want to know what is the prediction in the future. So that's kind of the setup, that's the problems we'll study. The outline is as follows. I'll talk about optimal prediction in general. I present lickers, consistent predictive state estimator, mixed lickers, then pattern discovery, and applications. So what do we have to do if we want to forecast optimal? Well, if you want to forecast something, predict something, you have to know the predictive distribution. So let's say you have some data D, that's the entire field, and there are total n observations. If I want to predict a new x, I have to know the conditional distribution of x given the data. The problem is, as I said already earlier, this is very high dimensional. Just the candle video, you have 1 million points. I don't want to estimate a conditional distribution with a million dimensional random variable. So we have to somehow limit that. And the solution to this is that you know something about spatial temporal dynamics. You know that things that can only influence each other in the future, right? So things cannot influence in the past, and they can only influence each other at a finite speed. When you remember the candle video, the smoke in the bottom left cannot influence the system at the top immediately. It needs time to rise, right? So I can reduce the huge dimensional V to a much lower dimensional L minus. And I'm talking about what it is. And L minus is a subset of D. And I know, just by the physical limitations of the system, that the conditional distribution must be the same. Because other points, it's impossible that they have an influence on X. And L minus is the past light cone of SU. And now what is the past light cone? The past light cone of the point RT are all the points in the past that can have an influence on RT. And I denote it with L minus for light cone and past points. The future light cone of the point RT are all the points that could be influenced by my current point. So for a two-dimensional system, think of this like as the images in the video, right? And I look at each pixel. So I look at the green pixel here. What is its past light cone? Well, those are all the points that could have an influence on this pixel. This is the red region here. What's the future light cone? Well, all the points that this pixel could influence in the future. And now you do this for all pixels in the video.
So is this application specific, or this is...
No, this is not application specific, right? This is for any physical system that you can think of. And weather, right? The clouds over there can influence me right now. It needs some time to come. In practice, we have to limit this to a finite horizon because, in principle, it's an infinite past and an infinite future. But we limit it to some, we cut it off at HP and HF, where we just look into the future this much and look into the past this much. And the speed of propagation is just how fast can those particles or points influence each other. Like how fast does does the cloud need to get here? And those are the control parameters. So now the prediction problem reduces to estimating these conditional distributions. I want to know the future given the past. So let's say I'm at this point. I don't know if you can see the red dot. You see that? Here's the red dot. I want to know what's the future look like, conditioned that my past looked like this. And I do it for all points in the image. But if you do it for all points in the image, again, it's large N, so that's very time intensive, and you didn't learn anything about the system. We want to learn something about the dynamics that's driving the system. So what we would like to do is we would like to find a function of the past light cone that keeps the predictive information to make optimal forecasts. That means we want to find a function eta such that the conditional distribution of the conditional eta is the same as if I would solve the original problem. Now there are different degrees of summary. It's kind of natural in data storage and memory. I want to summarize these light cones as much as possible without losing predictive power. So, or in another way, I want to find a function of the past light cones that is don't tell me more than absolutely necessary to make optimal predictions. So, well, it's for those who know, it's a minimal. We want a minimal sufficient statistic for prediction. Of course, nobody tells me what is this function. Right? I don't know eta. I don't know epsilon. I only know L plus and L minus. That's in the data. So how can we construct it? We first need this definition, which says two past light cones are equivalent if they predict the same future with equal probabilities. Meaning the conditional distributions conditional Li. If that is the same as conditional Lj, then we say that Li and Lj are predictively equivalent. It's important, and I try to show you this image, it's important that I'm not saying anything about the actual configuration of the past light cone. Those could be very different. All I care about is if they predict the same future. For example, in this image, we have the columns are past light cones, the rows are future. Right? So I have three different past light cones. These are the same, but they are different here. I have left, center, right. The left past light cone is this orange red, then the green, and then this blue red. They're all different, right? The left, and center, and right are different past light cones. But the future distribution of the left and the center one are the same. They're not the same here, because they predict different futures. So if all I care about is prediction, I don't care that this is orange and green, because they predict the same future. So I can summarize them into one and reduce the problem from 3 past light cones to 2 states that we'll see. So we reduce the problem from n to a smaller k. Now, how can we construct the minimal sufficient predictor? Well, Cosmo Shalisi showed how to construct those, and you do it by saying, let bracket L minus be the equivalence class of past light cones. Meaning, it's a collection of all past light cones that predict the same future as L minus. Is that clear? It's a set of light cones. And every one you pick will give you the same future. Now let epsilon take the L minus and map it to that equivalence class. That's the function epsilon. And the values it can take are called predictive states, and they have very nice properties. Namely, one, they are minimal sufficient. So now I showed you what is this epsilon. It's a minimal sufficient statistic for prediction. Meaning, I can replace the L minus here by the summary of the data, and hopefully reduce the dimension of the problem. And another nice property is that the future is independent of the past given the predicted state. So I have conditional independence. In particular, if I only look at the point at RT and SU, they are conditional independent given their states, which will become important in estimation later. So those are, these are the properties, and they were introduced in the discrete math, physics, literature, and there they typically have discrete fields. Right? You have particles that have plus minus 1, and then all you have to do if you want to estimate the function is you have to count. Right? How many are in this state, how many are in that state, and you compare. For continuous values data, you can't count anymore. Right? You have to develop some methods to estimate epsilon from continuous value data. And that's mainly the outline of what I'll talk now, of how can we estimate that from continuous value data. So in this one, I'll show you a consistent estimator. I'll not go into the technical details. I'll just explain how it works. You can see the details in the paper and archive. So we can think of this problem as a graph, right, with n nodes, and each node is a past light cone, and they are connected if they are equivalent. And so the adjacency matrix Aij is 1 if they're equivalent, is 0 otherwise. As usual, well, it's symmetric, so it's an undirected graph, but it's not only symmetric, it's also block diagonal. After rearrange, I mean, assume you rearrange the rows, of course. So it's block diagonal. Why? Well, because it's an equivalence relation. It's just not, it's not just a distance, it's a symmetric distance. It's equivalent, meaning if L, like the past light cone 1 is connected to 2 and 2 to 3, I know because of the equivalence that also 1 must be connected to 3. And also they can't be connected to another group. But then the clustering is trivial, right? Because the graph separates into these perfect cliques, and those cliques are the predictive states. So if I knew A, I would be done. Do we know A? Well, of course, we don't know A. Nobody gives us A. So how can we estimate A? Well, the definition of the link Aij is if they have the same predictive distribution. And that's a statistical problem. Given samples, you want to see if the distributions are the same. So you have the null hypothesis that says the conditional distribution of L minus is the same as the conditional distribution of Li of Lj. And you do it for all Ij from 1 to n. Now you can see already where we have a problem. If I have a million data points, I have a million times a million matrix that I have to first estimate. I'm not even talking about doing some testing. Only to get the matrix, I have to make n squared tests. And each test also takes additional computations to get this value. So we can't really do that this way. I can't test all entries in that matrix. For the short candle video, I would have to make 10 to the 12 tests. And then there's a statistical problem. Even in a toy example with small n, I can estimate the matrix, and it's symmetric because the test is transitive, but it's not, the test is symmetric, but it's not block diagonal. Why? Because tests are not an equivalence relation. So I can test this is the same, but they are not the same. That's the error you make in testing. So the matrix is not block diagonal, almost block diagonal, but not really. So the graph corresponding to the matrix is not perfect cliques. I can see some structure, probably like 2 or 3, but I would need an additional spectral clustering algorithm now to find the cliques in that matrix. I also don't know. So what is the light cone reconstruction of states? How does it work? There are 2 main, let's say, ingredients. One is you have a computational speedup because you can't estimate that matrix, element by element. And the other one is statistical. The computational speedup is the following. You say, you take your past light cones, there's a space of past light cones, and you cluster them with k-means, for example, into groups. And then into k groups, and k is much smaller than a. So you get a smaller graph. Now think of each group as a node in this graph gk. Now I'll explain in a moment what this assumption is. By this assumption, which you're going to see in the paper, all PLCs in that class have the same distribution. What does this assumption say? It's basically saying, well, we don't know anything about the process. We don't assume a lot about the process, but what we will assume is that if I have a past light cone and I have another past light cone with an epsilon apart, right? I don't expect the future to be completely different. I expect the future to be almost the same. The future distribution of one and the other will be delta apart. Now, as usual, well, the epsilon and delta are arbitrary, so I'll go delta to 0. So if I just make my epsilon small enough, I know that all light cones in the neighborhood will have the same distribution. But that's exactly what I want for the predictive states. So if I just make k large enough so that my clusters are small enough, I know that all of them have the same distribution. I don't know yet which one, but at least I know that they all have the same. So I can use them as a sample for that distribution. And then the statistical speedup. So I have now, instead of n, k nodes in the graph, but they're still not block diagonal. So what we do is we don't do spectral clustering, but we iterate through the list and merge. Right? I take the first one, and then I look at the second. Are they equivalent? I test it. If yes, you put them into this class. If no, you generate a new predictive state. Then you look at the third one. Is it the same to 1? No. Is it the same to 2? No. Oh, generate a new state. And you iterate through the list. This is much faster than spectral clustering. And the nice property is that the A hat is by default block diagonal. So I don't have to even do any spectral clustering. And you can show, under weak assumptions, more or less ergodicity, that this estimator is consistent. Ergodicity, and the idea is you need the system to not change too much, because you need a growing sample size in each neighborhood of the past light cones. So if the system doesn't change too much, then as n grows, you get more and more samples in each cluster. Now, how does it work in practice? Simulated data, conditionally Gaussian, x given d is a normal with mean d and always variance 1, and if this is less than 4, or a normal 0, 1. Now the state is not given to us by someone, but it evolves with the field. So I'll just put the equation here, I'll explain what it means. It means that the state at the green pixel, if you remember, the green pixel was current state. This is equal to the rounded difference between the average of 5 pixels with 2 steps before and the average of the 3 pixels 1 step before. And you can take any function you want. I just took this one. Okay? And this will give me an integer, and then I round it. So that will give me an integer valued state space. Okay? And because I decided that way, well, it's a triangle, 5 and 3. So the past is 2, my horizon is 2, and the speed of propagation is 1. If you simulate that, you get this. These are the observations. If you look at it long enough, you might be able to see some structure in there. But, well, it helps to look at this. This is the predictive state. This is the state space, not the predictive state space. So you can see, you can see these traces in blue and red patches. This is the spatial temporal dependence I was talking about. Right? In the field, I can really see that. And in practice, I only see this. I never see this. This should be simulated. The predictive state space is not D, because remember, it would, if D is 0, it's a normal 0, 1, but also if D is larger than 4, it's a normal 0, 1. So they get merged in one state, because they have the same predictive distribution. So that's the predictive state space, and that's the estimate that I get. Right? I only give it this. I don't tell it the horizon, I don't tell it anything. I just say, here's the data, figure out what is the predictive state space. It looks pretty good. I mean, you can see the same structures in here and there. How does it work on that was one example. How does it work on multiple runs? So we simulated 100 of these images, and I show you here the time series models. They're an in-sample MSE of 3, let's say. The important one is here. This is what we get. 1.8, 1.7. The truth is here. It's a normal with variance 1. So if I knew the state, I would predict, I would always make an error of variance 1. We're down here. So we beat by far the parametric versions. And that was in sample. Now out of sample, because that's what I actually care about in prediction, the parametric models are way off. They're at 4. Well, we are at 2. So we are better than those, but there's still room for improvement. And I'll show you now how we get even better in the MSE. That's mixed liquors. And now I'll talk a little bit more about statistics, because so far there was not a lot of statistics involved. So I always talked about forecasting, predictive distributions, but actually when we're doing inference, we would like to have a model for the joint probability of the whole process. So you can show that the joint probability of the whole process, and I used n tilde just to be consistent. N tilde are all observations, and you can show, similar to a Markov process, that you can factorize, conditioning and chain rule, that this is equal to the probability of the margin, this orange area, times these predictive distributions. So if you condition on the margin, the joint probability of the blue field is equal to this product of predictive distributions. Therefore, the log likelihood is proportional up to a constant to the sum of the logs of these predictive distributions. That's why we want to find these predictive distributions. And now since epsilon is a sufficient predictor, I can just replace that here. And that's how my likelihood now is a function of epsilon. And now, originally this was a function mapping to equivalence classes. That sounds a little strange maybe. So let's now forget this for a moment and think of the predictive state space as a hidden variable. So we have a state space S1 into Sk. Epsilon maps each outcome to the state. But epsilon, we don't know epsilon, so the state is a hidden random variable. But then we can write this product density as, if we know the state, we can write it like this, right? Because we don't know the state, but assume we know the state, then we can write it as equation 15. And this is the complete data PDF of a k-component mixture model, right? So where is epsilon in 15? And yet it maps to Si, so it's kind of here's an epsilon. But there's also another epsilon, and that is this indicator function. Is the randomized version of the epsilon. Because if the indicator function tells me what is the state at location I. The epsilon mapping tells me the state at location I. So how can we estimate epsilon? Well, we do a nonparametric EM and do a soft and hard thresholding on this indicator function. And that will give me an estimate of epsilon. And then there's nonparametric EM literature. You have some problems about identifiability and convergence. But all those papers basically say, well, in practice it works well. And I'll show you that it really does work well. So how can we maximize the joint PDF with respect to epsilon? Right? Directly we can do that because the SIs are not observed. And also, since it's non-parametric, I can evaluate the density because I don't know yet what it is. So I would have to, in a parametric model, I can just plug it in. But in the non-parametric version, I don't know. So, well, the first one, we know we have a hidden variable, so we use an EM, hidden variable mixture model. We use an EM algorithm. And for the second one, I follow what the literature does. You just approximate the component distributions by the estimate you have, and just plug it in. So it's just an approximate likelihood. But that's mainly the reason why you don't get convergence, because you plug in already an estimate. And yeah. Now, what is the E step? You have to take expectation of the state given the data and your estimate. But the indicator function condition on the state given the data is the probability that I'm in the state as J given xi and my past light cone times, oh, it should be here an f hat actually, times the log of my estimated. Now, using Bayes' rule, these are the weights, right? Using Bayes' rule, I can compute these weights by a kernel density estimate of the future. That's the predictive distribution. Here I use a Gaussian because it's high dimensional past light cone. And here we use just MLE, just count how many states, how many times is the state S shaped. In the M step, because it's nonparametric, you can really maximize the likelihood because you would end up with these delta functions at each point. So what they typically do is they say, well, in the E step, we got an estimate for the weights. So just use those weights for the kernel density estimate and plug it back in. That will not increase the likelihood. There's no proof that this increases the likelihood. But if you look at the trace plots, you get the usual, increase and a little bit wiggly maybe, just because the kernel density estimate doesn't maximize the likelihood. But it works really well in practice. In particular, here I show you one run on this field. I just give it the data and say, run the EM. It gives me in the end 9 states with those predictive distributions. Remember, they are normal distributions centered at -3, -2, 2, 3. So they look more or less normal. It's non-parametric, remember. I don't estimate any parametric model for the predictive distributions. It's non-parametric. The predictive states have this distribution. This is the weight matrix, the W, where a row tells me the probability that the light cone I is in state J, and every row sums to 1. So that's the probability distribution over the states. And the good thing about this forecasting problem is I can evaluate the performance. So I don't need even the increasing log likelihood. Normally you say, oh, if the log likelihood doesn't increase, we stop. That's the estimate. Here, I can evaluate the predictive performance and choose the best model I get. And that's my estimate. I don't have time to tell you why there are these bumps, but basically, you see that it increases to an optimum and then it drops. The reason is because I merged them. But the point is you can choose an optimal model. Now the good thing is, you have a good estimator if you don't know which one is which. And here I plot the true state space and the estimate. I didn't tell you yet which one is which. So the left one is the true state space and the right one is the estimate. And this is even out of sample. This is in sample, out of sample. And they're almost indistinguishable. And here are the residuals. The only difference between those two halves is that this is higher variance. Why? Because this is out of sample, this is in sample. But otherwise, there's no apparent structure in there anymore. If you do it for multiple runs, so how well do we do? This was the one I showed you before. It was 2 and 1.7. With mixed liquors, I even overestimate. I'm doing better than the truth. And my out-of-sample predictions are at 1.3. And there are ways where we can even make this gap lower. So now this one really gets you the predictive states perfectly, almost perfect. And now the last topic is the pattern discovery. And normally when you talk about prediction and pattern discovery, and dimension reduction, you usually would do it, I guess, the other way around. You would first do dimension reduction, find the signal, and then predict, because you don't want to predict the noise. So the idea for this automated discovery is you flip it, because I know how to do optimal prediction. I don't know how to do optimal pattern discovery, but I know how to do optimal prediction. I just showed you how to do that. And then, once you find the predictors, then let the structure of the predictors give you the structure in the system. Right? And this is the measure that we'll use. And Schließlich again introduced local statistical complexity, defined as the information that epsilon carries about the past. This is the information of the state and my past life. It's a comparable absolute measure of information interestingness for each point in space-time. And it's a property of the system. It's not because I defined, oh, I want to look for this frequency or I want to look for high variance. It's a property of the system based on information theoretic considerations. And what are the properties of that are, for discrete state space, you just have to compute the entropy of this event, minus log 2 of the probability. And for a perfectly constant field, complexity is 0. And for a perfectly independent field, complexity is 0. At the moment you have spatial or temporal dependence, you will be greater than 0. And it's measured in bits. It's the minimum number of bits needed to describe the predictive state. It's the entropy of the event that I'm in that state. Or you can think of it as the log 2 number of different predictive distributions. For example, if my entropy is 0, well, that means that there's only one predictive distribution. For example, if it's independent noise, well, there's only one distribution that I have to keep track of. And the entropy of a random variable with one value is 0. Now, if we go back to the mixture model interpretation, there, I think there's a nice property now that we can think of, or an explanation of what this complexity is of measuring. I can write the probability distribution of x as a, integrating out the state. And in forecasting, all we care about is the conditional distribution of the observations given the state. And once we know the state, I don't care anymore what the distribution is, I just want to predict. But for pattern discovery, the observations are actually irrelevant. I don't care about what the observations are. I want to see what is the system, what is important in the system. So instead of the distributions of each state, you look at the distribution over states. And you look at the entropy of this distribution, and you don't look at predictions of this distribution. And why? Well, because low probability states show interesting patterns, and high probability states show uninteresting patterns. If you have a video and there's only one pixel different, well, this will be a different state, and the probability that it occurs will be very, very low. So this will be the interesting part in the video. Now, how does this work in practice? So remember the handle, I'll show you a time-lagged version. So high values, red values mean more interesting. And yellow values mean less interesting. So what you can see here is that, well, what's interesting is the candle, and the smoke starts to rise. Well, it's there, you can spot at the top, and then this weird shapes up there. Right, and this is automatic. I didn't tell you anything. Just give it a candle video, tell me what's interesting. Now, since it gives me that for every point in space-time, I can compute I can compute summary statistics. For example, I can compute the average in each frame. That gives me, for each point in time, an average measure of how interesting is the video at this current moment. And then I'll plot the time series, and I see, for example, that in the beginning, okay, the candle is burning. Then someone blows it out, it increases, that's interesting. Then it drops, it's smoking down there, but most of it is background. Then the smoke starts to rise, we're here. Then you have this very regular shaped smoke up there. And then when it starts to form these swirls, then you start increasing with complexity. So you can give me a video, you apply the method, and I give you a kind of a summary statistic of what's happening in the video. What are the interesting parts? Then you can do an average over time to see what parts of space are interesting. Well, you can see the candle is interesting because that's compared to background, it's only a small part of space. And you can see that like the mean, you have the smoke here. And if you look at the standard deviation, low standard deviation means it doesn't change over time. Well, the candle doesn't change when it's there. The smoke changes, right? Sometimes there is smoke, sometimes there's not. And this whole region is white because, they blew it out from the right side. So the smoke went to the left. Okay? And that's why on the left it's more variation than on the right. And other applications. I mean, for the candle video, that's nice to look at, but it's not really helpful for some research. So you want to apply it to systems that you don't know anything about. And we don't know a lot about the brain. We know something, but not a lot. And so here we have fMRI data where they measure the visual cortex in the brain. And in this, they have two experiments. One is the harmonic stimulus, and one is not harmonic. In the harmonic stimulus, they show you these circles. They rotate in one direction, the other direction, and they also show them, in a flashing manner. And they know exactly what the frequency is of this stimulus. And it's a perfect sinusoidal, or well, not sinusoidal, but approximately sinusoidal stimulus. So if I know the frequency, then all I have to do is I'll have to look at my observations, take a Fourier transform, and look at this frequency. And those voxels that have a response at this frequency, well, then I'll see which areas are active. But that works well. You get these bands here. But again, this is because I knew everything. I knew the stimulus, I knew the frequency, and I do that. Now, how does it work if I just give it the data and say, do it automatically? So I use 80 frames, each one about 280 pixels. Those are 6 times 10 to the 6 dimensional data set. And well, you get those rings here. Right? You get them here, here. In all those summer statistics, I can see those rings. Again, I didn't tell it anything. I don't have to know the stimulus. And it still gets the same as if I knew that. And yes, you have lower signal-to-noise ratio, but that's just because this method is just so, it just needs more data to get the same precision as a perfectly matched filter technique. Now, it gets interesting if I have a stimulus that is not harmonic, and where I don't know what's going on. So if I have a non-harmonic stimulus, I would have to handcraft a method that matches the stimulus, and maybe I can do that and then look at the response. Then in a couple of months, I do another experiment with a different stimulus. I have to now sit down again, do a different technique. You have to every time do the same procedure for a different type of stimulus. And that's if you know the stimulus. But I mean, that's in a laboratory. In real life, there is not really clearly one stimulus that you know. So here we say, well, let's say we apply the Fourier method because that's what we know how it works, and we have that algorithm. It gives you those regions. So okay, two main regions, this one and this one, are interesting. So maybe now they might want to see, what part of the visual cortex is this, what part is this? If I apply local statistical complexity, I get these regions, which are first of all, they're 3 instead of 2, and they're also a little bit displaced from these. So the idea would be, the neuroscientists, that do the research on that data, on these experiments, I would tell them, take a closer look at those red regions and figure out what's happening there. Don't use these regions, because those are just some method that you think is good. This is this information theoretic quantity that tells me the properties about the system. And you see them in all 3 cases. They highlight all the same regions. The summary, discussion. I showed you Lickers, which is optimal nonparametric forecasts for spatiotemporal data. I showed you that they have much better forecasts than the standard time series models. They are fully automatic. You don't have to do anything. It figures out the parameters by cross-validation. I didn't show that because we don't have time. But you can do it by cross-validation. You figure out the parameters. I showed you the results for these nice spatial grids and videos, but nothing about light cones or predictive states requires this perfect grid that I can do it on any network. Nodes that have an influence on the current node. So You can apply to network data. Of course, you have the computational cost because you have to do it for each point. So you are limited in the systems you can study. And you have no convergence rates, no convergence guarantees for non-parametric EM. And I quote this paper that they say in their conclusion, there's the question of which if any function is maximized by our algorithm. And I showed you the approximate likelihood function, which was kind of maximized, but it's an open question in the non-parametric EM literature of what these algorithms are actually doing. And local statistical complexity is an automated method to discover patterns in spatial temporal data without, you don't have to tell it what to look for. It will figure it out by itself. And again, this is not restricted to this special rectangular grid. You can think of applying it to network data of disease spread, and you want to find nodes that are important for the spread of the disease. Those will have a different future distribution if they spread the disease than other nodes. Right? I should be able to do that once. So I want to thank my advisors, Cosmo Schulz and Larry Wasserman, Eli, Miriam, and Chris Genovese for the work on FMRI data, Loudon and the ML department for the invitation, and thank you.